Hi, this is Wendy Lightheart, and today we're going to learn about radical expressions. One example of a radical expression is the square root. The expression b equals the square root of a means that b is the unique non-negative number such that b squared is equal to a. We call b the principal square root of a. So for example, the square root of 64 is equal to 8, since 8 is that unique non-negative number such that when I square 8, the result is 64. Let's look at some more examples. The square root of 121 is equal to 11, since 11 is the unique non-negative real number such that when I square 11, the result is 121. What if we had the square root of a negative number, like the square root of negative 64? Well, this is not equal to any real number, since a real number squared will never be equal to a negative number. So there is no non-negative number that exists such that when you square it, you could ever get negative 64 as a result. So we just say that it's not equal to any real number. Now when we're evaluating radical expressions, it's important to understand where radical expressions fit into the order of operations. The order of operations, remember, is PEMDAS, sometimes called PEMDAS, or Please Excuse My Dear Aunt Sally, to help us remember it. And P is for parentheses, and E is for exponents, and those are the two categories that radical expressions will fall under. The operation that's denoted by the radical sign itself falls under the category of exponents. And the radicand, which is what we call the expression that's under the radical sign, is treated like an expression inside parentheses. So we would have to simplify the radicand first, since it's inside parentheses, and then we can perform the radical sign, because that would fall under the category of exponents, which comes next. So let's see how we can apply this to some examples. The square root of the difference of 64 and 25, notice that we have subtraction underneath the radical sign. So that subtraction is falling inside parentheses. You can think of it that way. So we would actually have to perform that subtraction first, and the result of that would be 39. And then we can actually find the square root of that number. So we perform the operation that the square root represents, and you might need your calculator for that. You probably do, because 39 is not a perfect square. And if you put that in your calculator and round it to 2 decimal places, then that's approximately equal to 6.24. Now notice this next example looks very similar, but the subtraction sign is outside of the radicals rather than underneath a radical sign. So we would actually perform the radicals first, so take the square root of 64, which gives us 8, and then take the square root of 25, which gives us 5, and then we would perform the subtraction after that, and the result of that would be 3. So you can see here how it makes a big difference on where that subtraction sign falls. So you have to be really careful to follow the order of operations properly when you evaluate these radical expressions, because as you can see, you get completely different results depending on where that subtraction sign is located. Now let's talk about cube roots. A cube root is another example of a radical expression. And the cube root of a real number a is written with, it looks like a square root sign, except for there's a little 3 that's written inside the check mark part of that radical sign, is the way I like to look at it. That's called the root number or the index. And so that would tell you that it's a cube root of a instead of a square root of a. And what the cube root of a is telling us is that the cube root of a is equal to b if b is the real number that when I cube it, I get a as a result. So very similar to the square root definition. So for example, the cube root of 64 is equal to 4. Since 4 is the real number that when I cube it, the result is 64. So let's look at evaluating some cube root expressions. The cube root of negative 8 is equal to negative 2, since negative 2 cubed is equal to negative 8. Note that this is different than with square roots, where if we tried to take the square root of a negative number, we saw that there is no real number that would be equal to, because you can't square any number and get a negative result. But you can cube a number and get a negative result, as we can see here. And so you can take the cube root of a negative number. Now, this expression, we have a negative sign in front of the cube root. So we would take the cube root of negative 1 first, and that's going to be equal to negative 1, since negative 1 cubed is equal to negative 1. And then we still have a negative sign in front of that. So that gives us two negative signs next to each other, and when we simplify that, we will get a positive 1 for our answer. Here we have the cube root of 64 plus the cube root of 27. So pay attention to where that plus sign is. In this example, the plus sign is between two radicals. It's outside of the radical signs. And so we would actually have to perform the cube roots first, and the cube root of 64 is 4, as we saw earlier. The cube root of 27 is 3, since when we cube the number 3, we get 27 as a result. And so after we perform those cube roots, then we perform the addition. So we add the 4 and the 3 together to get 7. Now with this next example, notice that the plus sign is underneath the radical sign. So we'd actually have to perform the addition first. And when we add 64 and 27, we get 91. And now we can take the cube root of 91. Now 91 is not a perfect cube, so you would need your calculator to calculate the cube root of 91. And you might need to find some help to figure out where your cube root button is in your calculator and how to use it. And I'd be happy to show you if you can't figure that out for yourself. So when you find the cube root of 91, you should get approximately equal to 4.5 when we round it to the nearest tenth place. Now let's look at an application of radical expressions. Police use the formula y equals the square root of 20x to estimate the speed of a car, which is represented by y, in miles per hour, based on the length, which is going to be represented by x in feet, of its skid marks upon sudden braking on a dry asphalt road. Use the equation to solve the following problem. A motorist is involved in an accident. A police officer measures the car's skid marks to be 45 feet long. Estimate the speed at which the motorist was traveling before braking. If the posted speed limit is 35 miles per hour and the motorist tells the officer she was not speeding, should the officer believe her? And we need to explain. So we're going to have to figure out how fast she was going to know whether she was speeding or not. And remember that y represents the speed of the car. So we need to find the value of y. And x represents the length of the skid marks. And so we know that the length of the skid marks was measured to be 45 feet. So we would take that formula and replace the x with the number 45. And then perform that multiplication. So 20 times 45 is 900. And when you take the square root of 900, we get 30 as a result. So it looks like she was going about 30 miles per hour. So of course the officer should believe her. She wasn't speeding. That's it for today.